So the first part is about computational, or the conservation laws is to do the computation basically. So it's more a mathematical excursion we're doing. And then the second part, I quickly wanted to show you on GitHub a little homework that you can do for next week, basically. The homework will be about parallelizing a simple summation loop. But we come to that in the second part. Let's first try with the notes. See if I can connect this one. So then you can see hopefully the whiteboard here. Good. So do you see that?
Yes, I can see that.
Okay. So what we're going to do is basically, let me quickly write down here what we're going to do in this class, basically. So in this class, we look at two equations. Those are like our two proxy equations that will help us with then any other geophysical equation. And one is the heat diffusion equation. And the second one is the wave propagation equation. So in order to solve these, then we're not going to solve them analytically, but we're using our numerical methods to do that. So we're using different numerical methods. To solve them. And the methods we're going to use is we start with the finite difference method. And that's probably the one most of you already have encountered. So what kind of method so far are you using? Like numerically? Tariq, Indra?
Well, I'm familiar with finite difference because it was taught in the Seismology 1 course. And
so it's usually the first method you encounter when you do a numerical method. Yeah.
Yes.
Some other methods you already saw?
well, I did see finite element.
Good. That's already a bit more advanced then, right?
Yeah.
Carly, Faustino, Ted, have you encountered some numerical methods so far?
Oh, this is my first time.
Carly? I cannot hear you, Carly. Something with the microphone is off.
You hear me, Prof?
Now it's good, yes.
Okay. I have experience with finite difference, but for finite element, I just little experience with that.
Faustino?
I have few experience with finite element, but not so much.
So especially then when you, in Martin's group, for example, when you want to do the earthquake rupture simulations, one of the code he's often using is the Sisal code. And Sisal is a discontinuous Galerkin code. So it's one of the more complex codes, basically, or complex methods that you can use, mostly coming from a finite volume expression. And that's something that I'm not necessarily going into in this class. So in this class, I want to start with finite difference because it's kind of the first method you start looking into. And then the next one is a pseudospectral called method. And pseudospectral methods kind of naturally extend the finite difference methods. We're going to see how that basically follows from a finite difference expression. Now, both of these two methods that we're going to start with, they basically use a numerical approximation of the differential operator. So these guys here, they use discretization of the differential operator. So for example, the grad of a function, the gradient of it, in order to compute the gradient, you actually approximate it numerically now with a finite difference scheme or a pseudospectral scheme. And then the other two methods that we'll look into is basically the finite element and then the spectral element methods, where spectral element is basically also, like, you can look at it like an extension, a higher order extension of a finite element method. And the difference here, basically, when you look at finite element methods, they use a so-called weak form of the equations, which is usually basically an integral of the quantities, and then we approximate numerically these integrals. So it's not directly anymore an approximation of the differential operator, but of the integrals that we will encounter in these weak forms. So that's the main difference between these methods that we're going to look at. We start with a finite difference, which discretizes basically the differential operator, and then we continue pseudospectral, and then finite element and spectral element, and those use weak forms. Now, the discontinuous Galerkin method, for example, in your rupture simulation with Sisal, it's a further extension of basically the spectral element. You can look at it. Spectral element is a so-called continuous Galerkin method, where then the Sisal code uses a discontinuous Galerkin method. The differences between these Galerkin methods we're going to see when we start, for example, with the finite element and spectral element methods. What Galerkin means. Galerkin is a way of setting up your basis functions, basically. And then discontinuous or continuous Galerkin means if you have shared points between elements, then either the solution that you're going to approximate is continuous between two elements at that shared point, or it is allowed to be discontinuous. So it's a further form of flexibility that you would have in a discontinuous Galerkin. So we come to that pretty much at the very end, but then I'm not basically going into the discontinuous Galerkin schemes that you will use, for example, in Sisal. That will be then a more focused method, I would say. So here the idea of the class is really just give you basically an introduction into these four different methods, so that you can develop your own idea how easy and how expensive the methods become. Where are the advantages, where are the disadvantages from one method compared to another method. So why do we use these numerical methods, for example, in seismology, where you can put seismology into simple words? You can say seismology in a nutshell. So what we do basically is we do simulations, numerical simulations, and then compare the synthetics with data. So if you want to put it in very simple words, that's seismology. So we do computations, compare those with the data we measure, and hopefully then advance our knowledge about the Earth. Good. So that's basically just a quick intro into the class, what we want to do. And now let's come to these two equations, heat diffusion, wave propagation equations. And in order to derive these equations, we start with the conservation laws. So let's start with the, let's say, more mathematical excursion now. And you're all PhD students, so it doesn't hurt looking a bit into this math part. It's a bit more advanced, I would say. Maybe for undergrads is more like look at it, but don't really need to understand it. For your PhDs, it doesn't hurt trying to go through it and basically make up your mind to see what this is about. So conservation laws, I put here the first one, conservation of mass. That's one of the conservation laws. So what conservation laws do you know of other than mass?
Energy.
Heat?
Yeah.
Heat belongs to energy, yes, conservation of energy.
Question of momentum.
Momentum, that's right. And you actually separate that momentum. It's into a linear momentum, which would basically playing billiard, playing pool, that's linear momentum, and then angular momentum, that's the rotation part. For example, the spin of a particle. So you have both conserved, linear momentum, the movement, and the spin. So that's angular momentum. And that's pretty much it, actually. So let's put this quickly down. So we have mass, we have linear momentum, conservation of angular momentum, and conservation of energy. So for us, these four conservation laws are basically enough. That covers pretty much all that we need for this class when we look at heat diffusion and wave propagation. You know some more conservation laws. There would be at least one more which is important. So it's about what is running these laptops.
The electric field.
It's the charge. The electric charge is conserved. Yes. So conservation of electric charge is also important, basically, because that's basically the conservation laws for electromagnetic fields then. But we're not going to use it for this class, since we're not going to look into the electromagnetic fields, although they would be important, for example, in geophysical exploration, etc. But that's missing in here, basically. What we can use are these four, and basically these are all so these are all the physical laws. We are solving for the wave propagation. So this is one star, which basically means we have, for the wave propagation equation, we need linear momentum, conservation of linear momentum. And then heat diffusion, or the heat equation, you see it's pretty much the conservation of energy that we're going to look into. Both will need the conservation of mass, and that's the reason why we start basically with conservation of mass. So we start looking into this conservation law and how that would boil down into an equation which gives us the continuity basically of mass. So these are the conservation laws, and then in order to, for example, solve the wave propagation, we also need constitutive relations, basically. So it's conservation laws plus constitutive relations. And if you heard, for example, from Hooke's law in elasticity, Hooke's law is one of these constitutive relations. And we need then Hooke's law basically to link stress with strain when we look at the wave propagation equation. And then we can basically solve that wave propagation. So it's the conservation laws together with a constitutive relation that allows us then to actually find solutions to these equations. Good. And again, that's all we do. In computational seismology or geophysics. Okay. So what we're going to do now is basically look at this conservation law of mass. It's clear so far? Good. So in terms of conservation law, it's not many. There are only 4 conservation laws. Mass, linear momentum, angular momentum, energy. And that already covers pretty much all in geophysics. Yes, you can have then electric charge, an additional one. If you want to look at electric currents, if you like, or electromagnetic fields like Maxwell equations, etc. Then you would also have the conservation of electric charge. But for us, these 4, that covers everything. Good. So it's really the basics we're going to start from, basically. So that's the basic assumptions, that these quantities are conserved. Good. So let's start with conservation of mass. And so what we're going to start with is basically a simple example. And the example is what is the rate of change for an area? And in order to make a little picture for that, so let's have some function. So f, which can be a function of position and time, x and t. And then we have a start time or start position. Let's say this is x, and this would be y, which is f of x of t. And then position, a start and end position. That function, and what we're looking at is the area below that function. Now, since that function can change with time, we can look at the rate of change for that area. So after a bit of time, let's say this function looks a bit different. Let me see if I can take a different color. So after some time, this function looks maybe like that. And so the boundaries changed a bit. And so the area below that curve, basically. So that would be at time t plus delta t, so a little time increment of the function f of x. Is that clear so far? Good. So the function is allowed to change with time. And then the boundaries, or the start and end point, we can say the start point is, let's say, a function a. So the position as well is a function of time, since the function f can change with time, with t. The start position basically is also a function of time, a of t, and this would be b of t. So if you want, this would be xa, xb, which itself is a function of time, basically, because the function is allowed to change. So at some point, these boundaries are allowed to move as well with time. Good. Now area, how is area defined? Well, area is the integral of the position xa, or in this case a of t, to xb, which is b of t, of the function fx of t over dx. So that's how area is defined, basically. The integral of that function from its boundary at one side to the boundary at the other side. So this expression is the area under the curve f, position and time x of t. Another question is, what is the rate of change? The rate of change of this area. So in principle, a very simple question now. So let's try and develop that a bit. So what do we mean by rate of change? So it's basically the time derivative of area. So it's d of dt of that area, basically. That's the rate of change of the area. So how is the derivative computed? Well, it's the limit, basically, 1 over dt. When you take dt to 0. And taking the integral at time t plus delta t, minus the area at time t. Dx here, sorry. So it's basically taking the limit of the area at time t plus delta t, a little time increment, minus the area at time t. And then you take the limit of it for delta t going towards 0. That would be the derivative. Is that clear? Just the basics. Good. So let's write out these terms a bit more, actually, what that is. And you see we have not only the function itself, the curve f, x of t, which is time dependent, unfortunately also the boundaries, the positions A and B are time dependent. And we have to take that into account as well when we take the derivative now. There's not only the area under the curve f, but obviously also the boundaries which affect then the rate of change of the area, how these boundaries move. So what we can do is basically it helps when we say, let's keep the boundaries fixed and look at the rate of change of the area for that integral, and then look at the parts where we now allow the boundaries to change. So split it into these parts basically. So that's what we're going to do basically. So we say, okay, let's keep the position A and B fixed at the moment here. And then we can take this limit inside and look at the limit of the curve f of x at time t plus delta t minus f of x at time t dx. So this one is now keeping the boundary fixed, and we also only look at the limit of the function, how the function changes between A and B. So that's the first term, and now we need to add these terms which have to deal with the boundary change. So let's look at the right boundary where we have b of t. So then we have the function at that position, and then we have the limit of b of t plus delta t minus b of t. So that would be the rate of change of the on the right hand of the right side, where we have b of t. And then the same at the left side, and you see if A is increasing, so if the A boundary would go towards the right side, it would destroy area. But when B moves towards the right side, it would create area. So there is a sign change between A and B, between the left and right side. So instead of plus here, we have a minus sign when we look now at the left boundary. So here it's f at the left boundary, A and t. And then we have the limit 1 over delta t of the right boundary at t plus delta t minus a of t. And that's it, basically. That's the rate of change of the area. So we split it into a part where we keep the boundaries fixed and then look at the part on the right side and the part on the left side. And you have to be careful with this sign change, basically. Good. Now these expressions we can put a bit together and rewrite basically this part. So the first integral, now instead of writing the limit, we can just take the derivative, and I use a notation like this for the partial derivative with respect to time. So this symbol here would be the same like the derivative with time, with respect to time, but it's a partial derivative. So in short, this would be just this one of the function. So that's basically the first integral that we had on top. Instead of writing now the limit, it's the partial derivative of the function with respect to time. So that's this thing here, partial derivative. And that's the first equation, first integral expression. Now, then the boundaries, again, instead of writing these limits, what we can do basically just write f of b of t. Now let's keep this t time. And now you see here b is a function of only time, only a function of t. If we take the derivative with it, it's not just anymore the partial derivative, it's just the derivative of the function. So here we can write d over dt of b, if you want. It's okay?
Yes.
So it's a bit different in the notation you see. On the left, in the first expression, first term, we have only a partial derivative. And the second is an ordinary derivative, basically. And then the third term, you see, it's going to be minus f of a d over dt of a of t. Good. So is it clear with the notation here? Good. So what we do is basically these last two terms, let's write them a little bit different. Let's keep the first expression, first integral, we keep it like it is, the partial derivative of the curve, f of x of t. And then again, we can write it a little bit different here. Let's see, this thing here, it's just the derivative of b. And we can just write it as b with a dot on top as a short notation. The dot above it means it's the derivative of that function. The function is only a function of time. It's derivative with respect to time. And again, this helps a bit shortening our notation. So then we have B dot times f of B minus A dot f of A. Good, but this thing here, we can basically write this as the flux term f of x of t times, if we would have a direction, that would be v times the normal A and B. So it's basically the flux of the quantity that goes in and out. So think of area as like being a quantity, and we see that in a second when we come to mass. And then if we just consider the fixed boundaries, then the quantity only changes with what the actual curve above changes. But then also we have a quantity that either can come into our area of consideration, or that moves out. And this is like the flux of the quantity that can come in or out. Good, so in principle, that's the rate of change of area is determined by the change of the curve within these boundaries plus the flux that goes in and out. You can look at it this way. Now let's come to mass, conservation of mass. That was our little example for area. Let's come to conservation of mass, and what we're going to look at is some sort of a volume. It can change with time. And what we look here is like a little parcel inside that volume. That's a dV. And that's a bit the difference between continuum mechanics and like classical mechanics or point mechanics. So in continuum mechanics, we look at these little parcels of volumes, how they change basically. Where in classical mechanics, you basically shrink everything down to point masses, for example. And then you look how that point would move. So in continuum mechanics, we expand that basically and look into volumes and little volume parcels and how they keep changing. That's a bit the difference between point and continuum mechanics. So how is mass defined? Well, you can take it as the volume integral of that volume. Of what? What do we need for mass?
Density.
Density, yes. Density is rho x of t. And then we integrate over volume. It's in 3 dimensions. Yes, so let's write this down. This is density. So that would be the total mass. So here, basically, what we have to know is the mass density, rho, which can also change position and time. So if you now compare basically how we defined mass and how we defined area, the expressions look very similar. No? So the function f of x of t, basically our mass density, rho, which depends on x and t. And we're going to integrate over the full volume, where here we just looked at the area basically. But again, in 1D, that's the same. And so what means conservation of mass? What is the rate of change now of mass? And it has to be conserved. So what means conservation of that quantity?
Not changing.
It means the conservation, that the quantity is not changing over time. So it means the rate of change now of this total mass is 0.
Yes.
So let's put that down. So conservation of mass. That is the rate of change of mass in this conservation law is 0. How can we put that into an equation? Well, if you look here on top, we looked at the rate of change of that curve, of the area. That's exactly what we have here, basically. So the rate of change would be d over dt of mass. Which is d over dt of our volume integral of the density x of t dx. That has to be conserved, which means it has to be 0. Good, and this quantity, that's the physics basically. The physical law. So now you see the exercise we made just before that is pretty much all we need now basically to express this conservation law. So the rate of change of mass is the rate of change of the volume of the density, the integral of the density. And if we write that down, we can write it as basically the mass balance. So let's write that a bit more exact. So we have the integral over density. Which is now, if you look at the terms we had for area, we have the integral with the partial derivative of the function, in this case of density, dv, plus this flux, basically, and this flux is the flux of mass that goes out of the boundaries of the volume. So here sigma t, that's the surface of our volume. And then we have basically the quantity times these normals of the surface. So compare with the terms for area. The first term is exactly the same. The partial derivative with time, Now instead of F, it's density rho. And the second, this flux term, is basically the flux that goes out of the surface of our volume. So it's a bit hard to draw you a good picture for that, but let's say this is f of t, and this volume can change with time. And then if you would look at the boundary, so the surface is basically this sigma t. It's the surface of the volume. And then you can, because it can change with time, you can look at a very small part of it, where you have say, a small piece of the surface, where you can have the normal to the surface. And then the quantity can move in a certain direction. That's V, basically. That's the velocity field in which the quantity moves. In our case, mass. It can move, let's say, in a different direction, let's say V. That's how the little mass parcel would move in that direction with V. So these terms, let's see. So the first term is like our fixed volume term. And then we look at the change of mass inside this fixed volume that we imagine. And then the second term is basically how much of the quantity moves into our volume of consideration or out. Or basically how much of it moves past the surface of the volume. It's like the flux through the surface. So is that clear?
Yes.
Good. So then basically, this is our mass balance. Basically. So this has to vanish basically. And now what we want is basically, we want to write these integrals to be in one big integral form. And in order to move from an integral over the surface to an integral over a volume, we can use so-called Gauss theorem or divergence theorem. So let's make this a little excursion. So Gauss theorem or the divergence theorem is basically stating that for a field U, and then you integrate over the surface, and n is the normal to that surface. That integral is the same like we would integrate over the divergence of that field. So again, there's a lot of new notation. You see, for example, this thing here. So if I put U with a bar below it, the bar below it means basically it's a vector. In 3D, it would be a three-dimensional vector. So this is short for, let's say, Ux, Uy, Uz. Then we have this nabla operator. It's basically the gradient. And again, it comes with a bar below. So it's basically the derivatives with respect to x, y, z. And then we have this dot between. So dot between, so it's a dot product between two vectors. Which basically now, if you write it down, would be dx ux plus y uy plus z uz. So it's a short notation for taking the dot product. And when we take the nabla operator, so this derivative, that's basically the divergence of u. It's called the divergence of the quantity u, which can be a vector quantity. Is that clear? Good. So here as well, you have also the dot basically between two vectors. Again, it's the dot product between two vectors. And because of all this, there's a new notation, the divergence, how we write it this way. There is a little PDF on GitHub, I will show you in a second, where I put all these kind of math expressions down. So you can use it like a cheat sheet to look up some of these expressions, how we define those. Good. Let me cancel this out. Okay. So let's come back to our two expressions here on top, where we have the volume integral and the surface integral. And you see what we're going to do is basically, instead of the surface integral, we rewrite it using Gauss theorem, the divergence theorem. And so let's do that. So what we can write is our surface integral here of density of V dot n. We can write this as a volume integral of the divergence of this quantity rho times V. Good. And now we can put everything under the same integral. So we have our rate of change of mass. That's the initial expression we had. Is now the integral over a volume of the partial derivative with respect to time of density plus the divergence of rho times V. So we can integrate over the volume. That's our rate of change of mass, and this has to be 0. And this has to be valid for any volume. Which means it doesn't matter how we integrate, over what boundaries we integrate. The quantity inside that volume has always to vanish, basically. So therefore, we have the time derivative of density plus the divergence of the quantity of density times the velocity field has always to be 0. So this is basically conservation of mass. And the equation is called the continuity equation. So this continuity equation is basically a conservation law expressing conservation of mass. Good. Is it clear so far?
Yes.
So it wasn't that difficult, no? So what we did is we just looked at rate of change of area, a very simple example. And you see the only thing which makes it a bit complicated is that the boundaries can move, which basically leads to this flux expression, flux terms that we need to consider. But then conservation of mass looks pretty much the same because it's an integral over density. Density can change with position and time. And again, conservation of mass then means basically that the total mass has to be conserved over time. So the rate of change of the total mass has to be 0. That's the physical law, basically. And if we write all that down, what we see is basically we come to this continuity equation. The rate of change of density plus the divergence of density times the velocity field has to vanish. So what we can do, just the last step to basically rewrite this continuity equation a little bit, is by changing our description, our point of view. What we did now is basically we fixed ourselves into a reference frame and then looked at how this quantity of mass would change within our reference frame. What we can do is as well, our point of view would be within this little parcel, this little dv here, and we move along with that little parcel and then look at how mass would change when we move along with it. So it's basically the difference between a Eulerian description and a Lagrangian description. Eulerian description means our reference frame is fixed and we look at how these things move in our reference frame. Or the Lagrangian description is we move along with that little parcel and look at how the quantity changes when we move with it. So that's what we want to do now. So the expression here that we wrote down is from a Eulerian description point of view. And when we change that, what we define is basically a material derivative. And then we can switch to a Lagrangian description of that. And the material derivative basically moves along with that little parcel. So our new derivative is like a capital D t, which is not only the partial derivative, but also this quantity of v dotted with the nabla, the differential operator. So this is what we define now basically as the material derivative. And you can think of this as being the time derivative in a Lagrangian description. So you see the second term, it's basically we move along with the velocity field and then take the derivative of it. So this measures the rate of change as you move with the flow v. This v is like a velocity field that we are placed inside, and we move along these streamlines of the velocity field of v, and then now we take the material derivative. Okay, look at the change of the quantity within our little dv parcel, basically. Yeah. Within our little volume parcel. And so you can think of this material derivative as the connection between Lagrangian and Eulerian descriptions. So think of it as being a connection between Lagrangian and Eulerian description. Personally, I find Lagrangian always confusing. Pretty much most of the time, I try and understand it more from a Eulerian description when we write these equations. The one on top, for me, is more intuitive than when we start now writing it with a material derivative. But you see, with this material derivative, it becomes a very simple expression. So we can rewrite then this expression of the derivative of density plus the divergence as being basically this v plus the grad of rho. And this is our material derivative of rho. But there is one more term that we need to account for. This is grad v. So it's then the material derivative of rho plus rho times the divergence of the velocity field, which has to vanish. Or if you want, if we are in a Lagrangian world, move along with the parcel, we see that 1 over rho of the material derivative of the quantity rho has to be the same like the divergence of the velocity field replaced in. So this is basically the same again, it's the continuity equation, but written from a Lagrangian point of view. So again, the rate of change of density is then equal to the opposite as the divergence of the velocity field. Good. Again, it's a bit a strange way of writing it. But the point here is now that material derivative of density, the conservation of density, you see it depends on the divergence of the velocity field we're in. And so if we have a fluid and a flow, basically a V, which is incompressible, and incompressible basically means that the divergence of V is zero. So for incompressible fluids or incompressible flows, the divergence is always zero. Which means that the conservation of mass, it boils down to having just the material derivative of density has to vanish, has to be zero. So that's basically the point here that we want to make. If you put ourselves into this Lagrangian description and we look at incompressible flows, where these velocity fields, the divergence of these velocity fields vanishes, then it's just very simple because the material derivative of density is zero. That's conservation of mass. And so incompressible flow, I told you, is basically what we see for fluids. So it's pretty much incompressible fluid. Means that the material derivative of density has to be zero. And water, for example, we can consider it as incompressible. So this holds for water, for example. For air, almost, let's say nearly. Not quite, because air is a little bit compressible. But not much, so it would be close to it. But that's just, yeah, if you want, it's one of the advantages. If you write it down as in a Lagrangian description, you can very quickly say conservation of mass for a fluid boils down to having the material derivative of density is equal to zero. Otherwise, if you want, you stay in a Lagrangian description, and then Eulerian description, and then you have this for the continuity, which is basically conservation of mass. Good. That's basically all I wanted to do in terms of mathematical excursion this morning. Is there some question about it? Clear, more or less? Let's try again if Shishu can be added. Good. Anyway, so that's the first conservation law now, basically, that you saw. Conservation of mass. What we will do in the next few lectures will be, we look at the other three conservation laws. Conservation of linear momentum, angular momentum, and energy. And then basically with all these four conservation laws, we can set up wave propagation and heat equation. The the conservation law I want to look next into is basically linear momentum. And then together with conservation of mass, we can derive the wave propagation equation, for example, the wave equation. So that would be the next step I want to do. And then quickly look at angular momentum. And finally, basically look at conservation of energy, because that helps us then to derive the heat equation. All of them, they basically rely on this one, on conservation of mass. And this one we just started with now. You see, in principle, it's very simple. You look at how mass is defined. You look at the rate of change of the quantity. And then you can basically write down an equation for the conservation of it. That's it. It's what we do with the other quantities. A quantity like linear momentum, quantity like angular momentum, or a quantity like energy. Good. Now, let me go to the next part, which is basically a little hands-on exercise for you. And for that, it's maybe easier, I quickly show you on GitHub what you will find. So, Sisho, can you hear and see that?
Yes, can you hear me?
Yes. So, Sisho, we have this class recorded. You can just look at the recording basically for this little math excursion, what we did for mass of conservation of mass. Hopefully
Okay.
you can just follow it then again when you look at the recording.
Okay.
So in this second part basically of this class, I quickly wanted to show you the GitHub page where you have the little hands-on homework for next week. So let me share that screen with the GitHub page. Should be this one. Good. So on GitHub, try to do that basically what I wrote you yesterday in the email. So I will put all the material, like all the homeworks, I will put into this repository on GitHub. And then once you have your local clone of it, you can just call a command called git pull, and it will pull down the newest material. So it's a way for you to get used to this Git versioning system. And GitHub by now is pretty much the standard. It's not the only one, but it's one of the biggest and easiest ways of putting things into the cloud and using repositories for them. So the idea of Git and GitHub is basically version control of codes. So when you have a code, you submit it, you tag it as your initial version, and then you keep changing the code, and Git keeps track of all these changes. So it's a version control system. We don't really need that feature in this sense for this class, because I just upload you material. There's not much version control on this part. But it's good for you to get used to Git, how you call Git, etc., how to set it up. So if you don't have an account, just make an account on GitHub. It's easy to do. You can then either fork, for example, this repository. So you have it under your own account, or you just clone it, whatever you prefer. You have here a little git quick material to help you get started with these git commands. That's something that Oleg was at some point quickly putting up, and he suggested how to like create your folders for the class, how you clone it. That's basically all that. Just a little helper for that. How you want to do it exactly is up to you. And then he actually continues. He gives way more, a bit more detailed explanations how you could connect your local repository with this upstream repository from my repository, or how you would start your own new code repository, where you would start from a scratch. Basically, you have a new code. This is how you would update your local. So local always means, for example, you have a repository on your laptop, and the remote one would be the one in the cloud on GitHub servers, for example. And this is how you could, for example, set up your own repository, add code files to it, etc., and then put it under this version control. Good. You don't need much of it for this class. Basically, all you can try is do this, basically. Make your own local folder and then just clone into that local folder. And next time I upload material, you just go into this folder on your laptop, called git pull, and it will get the newest material. It's basically all that we would need for this class. But it's useful to start getting used to it, how you would do version control. Then this is the little math primer, or this cheat sheet about math, something that we often use. So how you would, for example, define the dot product between two vectors. What would be tensor vector product? What would be a double dot product between two tensors? Or even dyadic products is also something we will encounter. How you would, for example, define the gradient or the divergence, something we just saw before, for example, divergence of a vector quantity or of a scalar quantity, whatever you prefer. And then here you also have the theorem that we were using, Gauss theorem, or also so-called the divergence theorem. We go from a volume integral of the divergence to a surface integral, for example. It's Gauss theorem. Then there will be some more parsecs. We don't really need that one. Chain rules. Probably you're already familiar with all these things. So a lot of it is maybe just more a reminder. And the rest of it is just the notation, basically, how I write it down in my notes, for example, with this bar below a vector. Here the vector is bold, so it's a vector quantity, and not just a scalar quantity, etc. That's a little math cheat sheet, for example, if you like. And then now for the homework, you will see this folder. So get that down onto your local repository, and in this little folder, the homework is basically parallelize a little for loop. The template I put you here is now in Fortran. It's a little Fortran template. It doesn't mean you have to do it in Fortran. Do it in any language you like. But the task is basically, you have a little loop. You have two vectors. You want to add them up, and then output the sum. The sum of these two vectors, basically. And the challenge now is basically parallelize this little summation. Make it in parallel. Because we saw that yesterday, parallelization is an important part when you do computations. So think about how you would parallelize this very simple loop, for example. See how you could do it in MATLAB, see how you can do it in Python, or Fortran if you like, whatever you prefer. So just want you to start looking into how you can parallelize things in the language you prefer. And here in the little README, it's basically mentioning what kind of parallelization models there are, for example. So, for example, to parallelize things in C, you would have options to use threads. To create multiple threads, basically, that's in C and C++ programming. And then you can run these threads in parallel on multiple cores on the CPUs. OpenMP as well is a way of parallelizing things. See how you would use, for example, OpenMP if you want with these directives, if you would use Fortran or in C. MPI, again, is a way of parallelizing things, and the main difference between OpenMP and MPI is OpenMP works if you run stuff on a single node with shared memory, where all the cores share the same memory, basically have access to the same memory. Where MPI, basically, it doesn't matter anymore where you are running the computation. It's basically you distribute now onto multiple nodes, compute nodes. They don't have to share memory with each other, but you have now to pass information between your parallel processes. So it's a message passing interface, which you do. So the main difference is between shared memory or distributed memory. Shared memory works with OpenMP. MPI, you need to do it once you have distributed memory, once your memory is separate from one node and another node. And if you want GPUs as sort of a parallelization as well, it's kind of a many-core parallelization. If you are courageous and want to start looking into how you would write it in CUDA, for example, you have option to do that, for example, as well, in order to parallelize things. So this graphic processing, you can, for example, write CUDA. There are compilers which allow you to write just directives in order to use them, or you use OpenCL, for example. That's another language to write stuff for GPUs. And then you can also look at different languages if you want. Look at some like Julia or Chapel, for example, which include parallelization under the hood. So it's pretty much just by the way of how you call a for loop or a do loop that it can parallelize it under the hood, basically, where you don't need to have some special considerations, special commands like with MPI, for example. So what I want you is take this little example, this Fortran example, use just this do loop, look at what it's doing, basically, summing up these two vectors, and then outputs the total sum of it. Just try and parallelize that in any language you like. You can do it MATLAB. In other years, for some students were writing it in Python. and then looked at how you can parallelize it in Python, for example. You can also do it in MATLAB, it's very simple. Or you just write it in using in Fortran with MPI or OpenMP, whatever you prefer. What I want you is basically look into how you can parallelize things. Try and find that out. And then I would say, write a little homework. Shouldn't take long just to parallelize this little loop. And we look at it next Wednesday, or let's say in a week from now, Thursday. Hand it in by next Thursday so we can look at it on Thursday. Let's make Thursdays our hands-on day and reserve Wednesday for more the, let's say, theoretical parts. Is it okay? Okay with everyone?
Yes.
Good. So you have it on GitHub. Just try and get it down from GitHub and then have fun with it. Yeah.
Professor, I have a question about the homework.
Hmm?
What kind of analysis we should do for the homework? Should we compare the time calculation before and after the parallelization? So,
if you want, yes. What I'm hoping for, just send me the code you wrote. Just send me the little code you wrote, and if you have timings, even better. But you see, for this very simple do loop, what you will find is once you parallelize it, it becomes slower.
okay.
So no worries about that. If it's parallelized and it runs slower than the serial version, doesn't matter at this point. The main challenge is just try and see how you can parallelize such a little computation.
Okay,
So yes, in the past, students tried to look at the timings. They found, oh no, it's slower, and then tried to invest a lot of time making it faster. But because in the little Fortran template I gave you, the vectors are very small. I don't know, 10 elements maybe. And if it's so small, it's hard to be faster when you run it in parallel, because you have an overhead of creating these parallel threads, which takes time. And then even though they run them in parallel, you have to basically combine again the results to get the total sum out of it, which again is taking time. So at the end, you have a slower version of your loop than if you just would use a single thread. But if you make your vector 1,000,000 elements, then you should start seeing the opposite. At some point, if the vector becomes longer, then the parallel version should at some point start becoming faster. But you don't have to. So don't worry if it's slower. Just think about how you parallelize that little computation. It's a way of looking into whatever your preferred language of coding is, see how you could add something that parallelizes that code. That's the whole, the main idea of this. And then just send me the code that you wrote. That's fine enough. And if you have timings to it, even better, but you don't have to. It's good? Good so far?
Yes.
Yes.
Then I think we're done for today, and we would see each other next week. So you have seen, well, today was the little math excursion, plus then these handouts, how they would look like. That's something that we're going to keep on doing, basically. So the next week we will continue with our conservation laws. We would look at conservation of linear momentum, trying to derive the wave propagation equation. And then as soon as possible, we would try and look at the little equation and use a finite difference scheme, for example, to solve it. And that's then again the hands-on part. That I'm going to show you theoretically how the scheme would look like, and you're going to implement it in a little code. That's the idea of this whole class, giving you an introduction into these equations and numerical methods and how you would implement it. Good? Good, then I wish you have a good weekend already. And see you next week on Wednesday. We keep the time. We keep 7:30 in the morning.
Yes.
For me, it's perfect.
Good. Let's be brave. Let's do that. Good. Bye, everyone.
Bye.
Enjoy the
Thanks.
days.